Well, it's our great pleasure to have Mike Jacox to give our second marine heatwave presentation following Dylan's talk last month. Mike received his PhD in ocean sciences from UC Santa Cruz in 2012. He has been working as a research oceanographer at NOAA Southwest Fisheries Science Center since 2017. He has very extensive research experience and a very impressive publication record on coastal marine ecosystem. Among various awards he has received, one is last year's U.S. Clever Early Career Award. Welcome, Mike, and now it's your.
All right, thank you very much for the intro, and thanks everyone for joining. I'll share my screen here. So yeah, I was asked to speak a little bit about marine heat waves, and I know that Dylan got you started along that track last month. And I actually wanted to take the opportunity to present some very hot off the press work that's actually just in review now, which is not so much predictability focused, but a new way of looking at characterizing heat waves and looking at their impacts. So let me just confirm that you can see my slides and that they're full screen.
I see the presenter view now.
All right.
There we go.
Okay, great. Okay, so I think that you got some background last month from Dylan, but just sort of to dive in, and this is a time series and sort of an example of what it looks like to quantify marine heat waves, and this is just a 10-year time series for a location off the Central California coast. These are SST anomalies taken from the OISST product. And the black line is the SST anomaly. And the bars are just monthly anomalies. So this is comparing daily and monthly anomalies, which are pretty consistent. But the bigger point here is that above some threshold, which is indicated by the dashed and dotted lines, you define marine heat waves. So where the bars are purple or the lines are red, those are events that have been defined as marine heat waves. And in this case, that's above the 90th percentile of the historical SST anomalies in this location. And so if you zoom in on one of these events, so this is the big one in 2014 into 2015, then there are a suite of metrics that have been commonly used to define these events. So one being the intensity, how strong are the SST anomalies in that event? Another being the duration, how long does it last from start to finish? So the key point for this talk is that these metrics define anomalies in a location. And so that, I think, when you think about impacts, is particularly important for things that are going to stay in that location. For corals would be a high profile, great example where you want to know they're not going anywhere, and you want to know what they're going to be subject to in terms of the intensity and duration of warm SST anomalies. But we also know, especially from a fisheries perspective, where I'm coming from, that many species move when there are these anomalies, and they move, in some cases, huge distances. And so this is a table from a paper by Cavol et al., again, discussing the Northeast Pacific marine heat wave, where they just looked at recorded range extensions of a wide variety of species during that event. And if you look at the far right column, you can see that for many of these species, you're looking at their distributions extending hundreds to thousands of kilometers farther north than they've been recorded before. So the motivation here is really to characterize marine heat waves in a way that's more relevant to this kind of response. Okay, so then the basic idea here, I'll just walk through the methodology of this calculating what I'm calling thermal displacement, is So you have a location here, and you have a time series, and for any time when you've got a marine heat wave, here I'm choosing November of 2014, you can look at the SST field spatially. So we're looking at the climatology for November on the left, the actual temperature in November 2014 in the middle, and then the anomaly for 2014 on the right. And the dots indicate that location where we're looking at the time series. And so in November 2014, there was this 2.1 degrees Celsius anomaly. So the temperature was 15.3, which was relative to the climatological temperature of 13.2. So then the idea here simply is to say, you know, in November 2014, it's anomalously warm. The temperature we would expect to see from the climatology is 13.2. So where is that temperature now? And so this contour here is where that 13.2 degrees Celsius contour is. And then we just look at how far do we have to go to get to that temperature. And so in this case, it's 838 kilometers away to the closest point with that climatological temperature. And so this distance is what I'm calling the thermal displacement. So that's the basic idea. And then what we've done is look at this globally over time and see, you know, what its patterns are and what sort of drives its patterns in space and time. So zooming out now to look at the global ocean, what I'm showing here is for the OISST record. So from 1982 to 2019, this is the median intensity of marine heat waves at each quarter degree grid cell in the ocean. So you can see a lot of spatial variability, obviously, where the more yellow colors jump out as regions that are subject to higher temperature anomalies during marine heat waves. So the Eastern Tropical Pacific jumps out, and you know, that clear El Nino signature. But there are also other spots like Western boundary currents that really jump out as a region of high intensity marine heat waves. So we can do the same thing for thermal displacement. It's computationally a much more intensive exercise, but basically we can still do the same thing, go through, you know, every heat wave for every grid cell and look at what the thermal displacement is and then summarize the statistics. And so this is now the median thermal displacement associated with heat waves globally. So again, we see considerable spatial variability and thermal displacements that range from tens to thousands of kilometers globally. And when you compare it to the intensity, you know, it's interesting in the ways that they align and they don't align. And so to sort of summarize it further, these are now just zonal averages at each latitude. And so if you look again at somewhere like the tropics and the Eastern Tropical Pacific, you see in both cases, you've got this region jumping out for both high intensity and large displacements. But in contrast, if you look at the Southern Ocean, if you look at the Gulf Stream, you see the opposite, really. You see these high intensity events, but you don't see a similar spike in thermal displacements. In fact, those regions are some of the lowest thermal displacements in the global ocean. So then the question is, what's driving those patterns? And to answer that, we look to just the spatial structure of the mean SST field. So this now in the top right is showing the gradient of the mean SST field. So the white contours are actually the mean SST field with 2 degree spacing between isotherms. And the colors are the gradient. So where the contours are close together, you're getting more into the greens and yellows where you've got strong spatial gradients in the surface temperatures. So the idea here is that simply that if you've got an anomaly during a marine heat wave, if the temperature gradient is very small, then you have to go a long ways to compensate for that anomaly to find that cooler water. Whereas when you have a strong SST gradient, even if it's very warm, that cooler water might be quite close by. So we can look at this with example locations. So again, I'm pulling out here, this orange dot is the Eastern Tropical Pacific. And then for that one location, we can look at every heat wave in the historical record and plot the thermal displacement as a function of the intensity. So there is, over most of the ocean, there is some positive correlation between the displacement and intensity for a given location. And in here, you've got intensities of say 1.5 to 4.5 degrees and displacements of 1,000 up to 2,500 kilometers. So huge distances. So to contrast with that, we can look at the Gulf Stream where you can see that SST gradient is really, really strong, much, much stronger than in the tropics. And this is what you get on that scatter plot. So you've got actually even more intense marine heat waves going up close to 6 degrees, and with the weakest ones being 2.5 degrees, but the displacement is almost negligible. It's tens to maybe 100 kilometers, simply because that gradient is so strong. And in fact, the gradient is also the reason why the intensity is so high in that region. When you have that really strong SST gradient in that current, if you get a little bit of a spatial shift, then you generate huge SST anomalies. So pulling out a couple more locations, now the tropical Indian Ocean, kind of similar to the Eastern Tropical Pacific in that the gradients are really weak, but in this case, the intensity is also weaker, so the displacement is smaller. And in another location in the Southern Ocean that falls more in line with the Gulf Stream in terms of being very little response in terms of thermal displacement relative to the intensity. And then the last examples I wanted to pull out are actually eastern boundary current systems, which are an interesting case study because due to the coastal upwelling in these regions, you have strong SST gradients, but they're also cold refugia. There are strong SST gradients, but the cold waters near the coast are surrounded by warm. So you can have to go quite far in some cases to get to that cooler water. And so these green and blue markers now are examples in the California current system and the Peru system. And they fall, somewhere in between these really weak gradient tropical locations and the very, very strong gradient regions. Okay. So then looking at some of the sort of more high profile events of recent years, we can dive into this a little bit more. So here, going back to the Northeast Pacific, I'm showing two locations, one again off the Central California coast and one up in the Gulf of Alaska. And for each of those locations, we can say, not just how far is the thermal displacement, but actually where is it? And so that's what these open markers are now, where they're showing for each heat wave what was the thermal displacement from those locations. So you can see, up the California coast, there's a range in terms of the distance, but they tend to be northward. In the Gulf of Alaska, you get a mix of sort of north and westward displacement. And when you look at the mean SST fields, which is what that background color gradient is, you can see why, right? The coldest temperatures are to the northwest towards the Aleutian Islands. And then just to pull out a few of the biggest signals. So 2014 again jumps out. This Northeast Pacific marine heat wave gained so much attention. Off California, 2005 is another one that jumps out, and this was a year where there was a very delayed onset of upwelling that led to very warm anomalies and cascading impacts throughout the ecosystem that has been much discussed in the literature. So this is now looking at the Northwest Atlantic off the east coast of the United States. And I'll first just note that the box here is a lot smaller. So when you compare this to the Northeast Pacific, the distances are actually much smaller than they are in the Northeast Pacific. So that 2012 event, which was, there was a paper by Kathy Mills that I think was one of the ones that really kicked off this recent wave of interest in marine heat waves. In that case, there was the thermal displacement is, I think, about 300 kilometers, which is consistent with shifts that they saw in commercial fisheries. But on the East Coast, given the political geography, that smaller shift had big implications in terms of how states are dealing with the moving fisheries. And then you look somewhere like out in the Gulf Stream extension, where again, due to that SST gradient, you have very, very little thermal displacement, even in the strongest events. And then back to the Eastern Tropical Pacific, not surprisingly, some of these most prominent El Nino events jump out as the times when we get the largest displacements. And then if you look at a location along the equator, of course, sometimes the displacement is to the north and sometimes it's to the south. And these distances, again, in this case, are up to 2,500 kilometers. And the last example I want to show is just the Australian waters, where there's been a huge amount of research on marine heat waves. And with examples off Western Australia, off Northern Australia, and in the Tasman Sea. And this is, again, if you look at that background color, there are these pretty strong meridional gradients in temperature and displacements that are small relative to the tropics or the eastern boundary current systems. And I could be wrong about this, but my impression has been that the discussion of impacts in Australian waters has been much more focused on corals and seagrass beds and things like that, and less so on distributional shifts. Whereas in some of these other regions, the distributional shifts have been discussed a lot more. All right, so then I just wanted to move on and think or talk a little bit about this metric, this thermal displacement, in the context of future warming. So to set the stage for that, I just want to sort of briefly discuss how we think about marine heat waves under future climate change, because it's a point of disagreement in the literature and I think in the oceanographic field. But here is, going back to my California example, this is now projected sea surface temperature at that location relative to a 1982 to 2011 climatology, the future change. And this is taken from a regional ocean model projection that was forced by the IPSL climate model. So when you have this future change, relative to zero is your climatology. So just sort of schematically, one way that people have thought about marine heat waves is to say, where is that 90th percentile threshold historically, which is what this dashed line is. And that's what you've used historically to define marine heat waves, and you keep on using it in the future to define marine heat waves. And so then the red is now marine heat waves under this definition. And so this is the basis of, I'm sure you've seen papers discussing the increase in frequency, duration, intensity of marine heat waves in the future. And this is the basis of that. It's just this warming signal, where if you choose a fixed threshold, then everything gets warmer. Every percentile gets warmer. So you classify more and more as marine heat waves. So my take on this is that I think it's not the right way to do things, that it's misleading and I think a little counterproductive. So the way that I'm talking about it here is, of course, we have a warming trend, right? And you look at the threshold relative to that warming trend. And so now these are your marine heat waves, since a wave is really variance. So you have marine heat waves and you have your marine warming, and you keep things separate. So when I talk about changes in marine heat waves, this is how I'm talking about it. So now to sort of shift from just looking at anomalies to looking at thermal displacement, I'm going to sort of do this in a schematic way where I just change the labels and the title on the same time series, where now instead of thinking this as a temperature at a location, this is now the latitude that you have to follow in order to, or latitude that you would go to in order to follow that historical climatological temperature. So this is saying that as you shift, as things get warmer and warmer, you're going farther and farther north in the mean, and also that there's variability about that mean shift towards the north. And so again, there's a mean displacement, which I'll touch on later. That's actually been discussed in the literature and in what's called climate velocity, if you've heard of that. And then there's this marine heat wave displacement, which is relative to that mean change in the displacement. And so my interest is, well, you have, historical displacements, which we've looked at, and there's future displacements, and, will there be a change in the nature of those? Okay, and actually the way that I'm looking at this is not to look at the change in thermal displacements due to changes in the variance. It's actually just to look at changes in thermal displacement due to the mean changes in temperature. So if you look at future projected SST changes, so this is just the CMEP5 ensemble mean under the RCP 8.5 scenario, end of century minus our historical climatology. The important thing here is not so much the degree of warming or whether it's correct even, but just that it's spatially heterogeneous. So you have spots that light up for much stronger warming, like the Northwest Pacific, Northwest Atlantic. And you have other regions like much of the Southern Ocean or the North Atlantic, the high latitude North Atlantic, where the SST change is much less. And so what that does is it actually changes the sea surface temperature gradients, the mean sea surface temperature gradients in the ocean. And that translates to changes in this thermal displacement metric. So this map is, I don't know, it's kind of busy, I guess, but some key takeaways are that you get displacement changes of both sign, which can reach under the RCP 8.5 scenario about 30% of the historical value, and that there is this spatial structure, which we can say sort of some things about qualitatively. So one, looking back to the Eastern Tropical Pacific, this is a region where in the models at least, which, may have issues in this region, but the projected warming is relatively strong in that region. And so what that does is it actually enhances the sea surface temperature gradient so that in the future, when you have a heat wave in that region, cold water is not as far away, and the thermal displacements along the equator actually are reduced. If you look at the North Pacific, you have this enhanced warming to the north, which is where, you would, when there's a heat wave, you would normally go north in the North Pacific to find cold water, but in the north, the warming is enhanced. So you're having to go even farther. So that's why much of the North Pacific, you see positive changes. And you see the opposite in much of the North Atlantic, at least in the sort of central and eastern parts, where you have this relatively weak warming in the northern latitudes. And so that poleward gradient is actually getting reduced and reducing thermal displacements. The same is true for much of the Southern Ocean. So those are the main things that I wanted to present about this this new metric and how we've looked at it. And then I think this is sort of a, you know, first cut at looking at it, and there's a huge amount that can be done to expand on this work. So I'll just touch briefly on some of the avenues, or the obvious avenues. So one is to, you know, actually relate this to movements of marine species. And this has been done with a, you know, a similar analysis that I mentioned, this climate velocity, which looks at these spatial shifts on climate change timescales. So these are figures from a paper by Malin Pinsky et al., where they're looking at this climate velocity, which is this sort of long-term movement of isotherms across the surface of the ocean, or sometimes in depth, and seeing whether marine species track those. In a lot of cases, they do. Another obvious extension is to move beyond SST. So, you know, SST is certainly a useful proxy for a lot of things that are going on in the environment and a lot of responses that marine species have, but it's not everything. And it certainly isn't everything that marine species respond to. So you can imagine further constraining these displacements, not just by where a suitable temperature is, but or a suitable surface temperature, but, you know, allowing movements to greater depths in some cases, or constraining it to regions with adequate oxygen, with suitable prey, et cetera. And then lastly, especially, you know, given the nature of this panel and my interests, we'll want to look at predictability and see how the predictability of this thermal displacement relates to predictability of other marine heat wave metrics like intensity that we normally think about. And I think it's interesting in that it incorporates both the magnitude of anomalies in a region and also the spatial structure of the temperature field, which you know, there may be predictability in those two things that is not necessarily perfectly tied to each other. You know, you may get some predictability in those things that's somewhat independent. And I'll stop there and gladly take any questions.
Great, thanks, Mike. So a reminder, if you do have questions, just feel free to unmute yourself and ask your question out loud, or you can type in the chat box and I'll read out loud for you.
Hi, Mike. This is Antonietta. I have a question. Actually, two questions. One is a technical one. So in computing this thermal displacement, so you start from a given point where you have an increasing temperature, and you are looking for another point where the temperature was the same as before the anomaly started. So how are you looking in all directions? And is this, you may not have just a unique solution?
Yes, so I'm looking in all directions. So basically, the way the calculation proceeds is the climatological temperature becomes a threshold. So I'm looking for anywhere where the temperature is at or below that temperature. Mm-hmm. And so that's all, you know, sort of accessible initially. But then I also constrain it so that, you know, you can't. So if you're in the Eastern Tropical Pacific, in some case, the Western Tropical Atlantic might be the closest temperature, right? So there are certain sort of continental barriers and things like that. There's some details of excluding, but yeah, it's basically looking in all directions, the closest point with that temperature.
The closest point, okay. Yeah, yep. And then, so going then to your future work and how to connect these metrics to actually the movement of marine species. So I appreciate the fact that you are intended, or you think that it's important to look at other variables, because you know, there are I think each species is attached to a given habitat. So some species may like actually the bottom. So could be the bottom temperature more important, or like a rocky environment. So like where they like to hide. So in some sense, it's really a very multivariate type of problem, where for each species you would have to try to include some of these other quantities that define the habitat that is ideal for that particular species.
Yeah, absolutely. And I think in any of these things, you know, it's true of the sort of traditional metrics as well, that they don't just mean something for marine species. You know, for any species, you have to think about the thresholds and the responses and all these kind of things. But I will say that, you know, while obviously SST isn't everything, it is powerful. You know, when you look at ecological models, it's pretty consistently the best predictor or one of the best predictors of species distributions. And a lot of species do have to be near the surface. You know, not everything can just go deeper.
Yeah.
So I think there's value in this sort of first iteration, and I think there's a huge amount of room to build on it.
Hi, Mike. This is Sean Elipo. Can you hear me?
Yeah.
Hi. Thank you for your presentation. I have a quick question. So as you showed at the beginning, you know, that change of temperature that you call a heat wave, a marine heat wave, in Western boundary current regions, it has to do with a very different mechanism that in some other part of the world. Like in Western boundary current region, it seems to me that it's pretty much just a meridional displacement of your current base. So, and you know, you're still in a region where the ocean is heating the atmosphere. So I was just wondering if you've tried to relate in other regions those heat waves to heat fluxes, to try to understand the mechanism, if you're looking at air-sea heat fluxes or if you're just looking at meridional displacement of fronts.
Yeah, so I mean, not as part of this work. I've done that in the Northeast Pacific to look more mechanistically at the drivers of heat waves and their evolution, and others have certainly done that in other regions. And I think Dylan talked about that last month as well. But this analysis is strictly looking at the temperatures. It's not mechanistic at all.
Okay, thank you.
Hi, Mac. Hi, this is Wei Liu from UC So yeah, it's a very nice talk. I'm very interested, especially I agree with you about the importance for the future climatology SST pattern. So my question is that, shall we consider about the change for the future climatology in a moving sense, like you showed the last 30-year SST change? So if we want to focus like the every decade or every year, so shall we move the mean climatology every 3 decades? For example, you know, for the heat wave in 2020 to 2050, shall we use the mean climatology for the 2020 to 2050?
Yeah, that's my take. I mean, so the way I did this, even for the historical period, I calculated the anomalies and then detrended them, because there are trends even in the recent decades. You know, I think that there are lots of applications where the total temperature change is important, both the trend and the variability. But I think that, you know, waves are the variability. So you should, if you want to look at the heat waves, you should be removing the climatology that's relevant to the period you're looking at.
Okay, thank you very much.
Sure.
Yeah, I had a question about the climatology, because those plots you're showing with the trend, is that just like for one region? I can't remember what region was that for.
Yeah, that's just one location off the California coast.
Right. Yeah. So and to be clear, I don't have an answer for what I'm going to ask, but and I struggle with this in terms of ENSO thresholds, because we have this half-degree cutoff. And what we're forced to do is use the last 30 years as our climatology. The problem with that comes right before we're about to do an update of that climatology. There's usually kind of a big jump. And so we're trying to figure out ways to kind of smooth through that. But the problem here is that but there may not be, in other words, you almost, in order to understand marine heat waves going forward, kind of have to assume what the climatology is going to look like going forward. And that can be challenging in certain regions which do not, smoothly vary.
Well, I guess I'll wait to let Matt jump in for why you shouldn't use 30 years, like you're saying, but
Well,
assuming that
I'm
one
not
can use
picking that, but a lot of people do.
Yeah. Yes, a lot of people do. So assuming you use 30 years, my approach, moving into the future would be that you just have like a running 30-year climatology, in which case I don't think that you should get big jumps.
That's true. But I think, users telling them that the value is going to change every year can be a bit of a challenge.
Yeah, fair enough. The other thing you can do is use a fixed climatology and then detrend the anomalies. But when you go far out into the future, there are clearly changes in seasonality that might make that less appropriate.
Yeah, I agree. Yeah, it's
So,
a
Mike,
tough problem. I think a lot of people are struggling with this. So I don't know the right answer here.
Mike, I was kind of curious about something along those similar lines. So this is more of a Lagrangian metric, basically, whereas these other metrics are more Eulerian. So do you capture events, say, over the last 50 years that you don't capture with just kind of an SST sort of metric? We've been looking in the Northeast Pacific, for example, and if you look at kind of the longer term SST variation, you can see that there are certainly periods where there's a very rapid increase in temperature, which you could call a heat wave, but it's relative to a lower baseline, so it doesn't hit some threshold over 30 or 50 years. But potentially, would you capture those events with this sort of metric?
That's actually a great question. The way I've done this, I've kind of precluded myself from being able to answer that because the first step was that I defined what is a heat wave based on the Eulerian, the fixed location analysis, and then I looked at the thermal displacements during those events. So the more comprehensive way to do it, and 10 times more computationally expensive, would be to calculate the thermal displacement for all times, which is a great idea, and then see if there are times when that metric jumps out that the local SST anomalies don't necessarily jump out that much.
Okay, so that might answer my other question, which is if you're actually interested in predictability here, you'd like to have some estimate of the noise, essentially, kind of what you get from random variation. But do you have any estimate of that, or you've only looked at isolated warm cases?
I've only looked at the warm cases, but you can, your other bound is if the temperature is at the climatology, then the displacement is 0. So I think probably just the warm cases give you a sense of the noise. If you look at something like the Gulf Stream, then the noise is huge, right? I think the signal of the noise is probably really bad, and in other regions, it's probably a lot better. And now that I'm talking through this, it makes me think that the predictability is probably similar to what it is for SST anomalies in general, thinking about it from a signal and noise perspective.
I think that would be something you might want to look at. I know that the only other analogous kind of measure I can recall is Young Kwan and Claude Frankenmuth had this measure of the Oyashio extension index, which was based on essentially a shift in the gradient of the Oyashio. But when you take their time series and regress it on the SST, it basically just looks like pretty much the second EOF of SST again. So it's not clear to me that it was entirely an independent metric. I guess I'm kind of wondering about that here too. It's whether, is it actually an independent metric? If you computed this from all time and then did EOF patterns of the metric, would you basically just recover SST EOFs? You know, what different do you get from a diagnostic perspective? From a prediction perspective, I can see how this might be superior, because it might be that, yeah, you're trying to predict, this is closer to a quantity you'd actually like to predict maybe than just a local change in sea surface temperature. But from a diagnostic perspective, do you have any sense of what different it gives you?
Well, I think so. If you look, if you look at the correlation of this metric point by point with the SST anomalies, there are lots of regions where they're positively correlated and even strongly positively correlated. But there are also lots of regions where the correlation is weak and even insignificant. So which means that you can have, well, it simply means that the strongest or the largest displacements can be in times when you don't have the largest SST anomalies. And I think that's dependent on the spatial pattern. It's probably largely dependent on the spatial pattern of the climate modes and where you are. So if you imagine like, if you think about like the sort of leading mode, like an ENSO or PDO pattern, if you're in a region where you're shifting between the positive and negative values of that mode, then you're going to get a very different response in the thermal displacement than if you're like in the Eastern Tropical Pacific, well inside sort of a single signed region of that mode. So I don't think it's generalizable spatially.
Hey, Mike. This is Haiyan. Since we only have like 15 minutes left, I want to catch, and you're from the Southwest Fisheries Service Center. I want to catch the opportunity to ask you to give us, with the panelists, some recommendations and suggestions on things like you mentioned the predictability of the marine heat waves, and in your talk, you mainly focused on the thermal displacement. But would you please give us some recommendations and suggestions if we want to pursue predictability study? How could the modeling community help? And what also I think we'll be very interested to hear your perspective on the current status of the marine heat wave predictions at your centers and the related operational efforts.
Sure. I mean, I guess I can say generally that, in fisheries, the approach is that people build ecosystem models and they take physical oceanographic inputs generally as, they take physical oceanography as inputs or climate model output as input to those models. So any skillful forecasts, any skillful predictions that can be generated in those physical fields will be hugely appreciated by fisheries, and they have models that they're ready to sort of run on those forecasts. There's been a lot of work to sort of start building infrastructure and tools where fisheries relevant projects or management relevant products are running off of physical inputs, and they're running in real time, or they're sort of proof of concept based on historical information. And to the extent that we can skillfully forecast, they can be run in forecast mode as well. To heat waves specifically, it's certainly just like a area of intense interest right now in fisheries. I don't think of it as being that distinct from just temperature prediction in general. I don't think it's a distinct problem. But but it certainly gained more attention that way. I think there's a big question of what makes one of these events impactful. You know, so like this 2019 event that Dylan talked about, by a lot of metrics, it was sort of on par with the 2014-15 in terms of its size and its intensity. It didn't last as long, but it also doesn't look like it was nearly as impactful. So, you know, thinking about why that might be, from, you know, just the persistence of it to the depth penetration of anomalies to what also is going along with those anomalies, you know, the biogeochemical signatures that go along with temperature anomalies or things beside temperature that might drive marine species responses, I think are of a lot of interest and are sort of key to furthering our understanding of the impacts.
So I have the impression that here we're focusing on the temperature, but Matt and other people who have mentioned, it's kind of still I had the impression that it is still unclear whether the forcing or the drives are from the atmosphere side or the ocean side. Do you have any what is your take? Like how should we if we want to pursue predictability study and look for the source of predictability, what would be your way to tackle the problem?
Well, I mean, I think, you know, things like what Dylan, I think, presented last week, you know, heat budgets of these events are hugely beneficial. You all are probably in a much better place than I am to say what drives these kind of events. I think it's regionally dependent. But yeah, those kind of historical analyses of heat budgets to figure out what the drivers are really beneficial. And then I think doing those same kind of analyses in the forecast to see, you know, what sort of elements of the heat budgets they're getting right or missing is key to linking the forecast scale to the predictability.
I have a little, I think like for Dylan's talk, he's more focusing on like multi-year or at least lasting a season, like the time scale. I wonder whether you could distinguish whether you're focusing on the same time scale as Dylan's.
Yeah, I think so. I mean, I did this analysis with monthly data and did some sensitivity analysis to show that sort of the findings I've shown here aren't sensitive to whether you do it with monthly or daily data. But when I think about the impactful marine heat waves, I think of them being certainly a month or longer, which is, I think, sort of the similar kind of climate perspective that Dylan was coming from.
Thank you.
So I had a quick question. This is Charlotte Dumont from the Process Study Model Improvement Panel. And it sort of gets to this question of what time scale of predictability is useful. And specifically, I'm thinking about the S2S database, which is a database of, historically, it's been atmospheric output variables from forecast models that generally cover 30 to 60-day forecasts. So, but the ECMWF and one or two other models have recently added ocean output variables to their to this database. So things such as the upper ocean heat content, surface salinity, SST, surface currents, mixed layer depth, several other things. And so I'm wondering, is there any value in looking at forecast skill on, say, the 30 to 60-day time scale with this database, or is that still a little bit too short of a forecast period for you to really get to the answers that you need?
It's absolutely useful. So I've just pulled up a slide from a different presentation, but this is a plot actually from a paper by Desiree Tomasi and others. But this is like a typical STOML plot, but it's mapping fisheries operations onto that space-time continuum. And so the point here is just that, yeah, if you look at days, weeks to months, there are fisheries decisions being made on those timescales.
Mhm.
So like ones that jump to mind that we're working with, one is that there are concerns about ship strike risk. So whales getting hit by ships, and the appropriate timescales of forecasting for that would be something like 2 weeks,
Okay.
where shippers are planning their routes, and they can be avoided. Yeah, there's closures that can be enacted if we can predict where certain species are that we don't want interactions with and things like that. But I can, if you want a sort of more specific list, you can certainly contact me and I can give you examples.
Okay. Are you aware of any efforts to use data from that database for these types of studies?
Well, I am part of an outstanding proposal to try to, I guess it's not as application focused, but yeah, looking at subseasonal, the S2S and sub-X outputs for predictability off the West Coast with sort of fisheries applications in mind.
Mm-hmm.
But there's definitely been more work thus far, largely because of the Climate Program Office funding on the seasonal timescale.
Okay, great.
Yep.
All right, well, that's great to hear. Thank you.
Sure.
Hey, Mike, this is Dylan Amaya. I had a quick question for you.
Hey, Dylan.
First of all, great talk. I had a question about that Penske figure at the end of your presentation. So that, if I understood it correctly, and huge caveat here, I know close to nothing about fisheries, but I'm trying to learn. So this is showing sort of the long-term change in a select set of species in response, presumably in response to the long-term shift in sort of their thermal comfort zone, just due to climate change, basically. Is that the idea?
Yeah.
Okay. So
it's saying their thermal comfort zone stays the same, so they move with the climate to remain in that comfort zone.
Right. Okay. So this Penske paper and presumably others are looking at sort of the mean thermal displacement of critters due to the mean change in SST, and what you're looking at is sort of the variability in the thermal displacement in response to the variability in climate, which is it's a really cool concept. But I guess my question is, and sort of branching off what Antonietta brought up earlier, is the variability in the range of a species, are they going to move in the same direction as they would in the mean? And does it have to be the same thing? I mean, are they always going to follow the sort of the path of least resistance and go to the, if temperature is 100% what drives their movement, are they always going to go to the shortest distance between them and that nearest isotherm, that sort of thing?
Yeah, so that's a fair question. I mean, that kind of assumes that they're all knowing in terms of where the closest water is, right? Where they may actually, maybe there's some memory that would have you move north, or maybe it's more following gradients. But yeah, I think it would be naive to say that they're just going to go to the closest point. And I think what you can't necessarily see from this analysis. So if I pull up some of these examples, this is showing the closest point for each event, but it could be, if I don't know if you can see my cursor, but if you look at the Northeast Pacific here in the green, and in 2014, the point that's pulled out is pretty much straight to the west. In a situation like this, you could also have a point that's straight to the north and is only slightly farther away, right? And it wouldn't be the one identified here, but it would be another option. So I think, I think this is where sort of looking at the individual events against the fish data would be very informative.
Right, and that was going to be sort of my follow-up question, is if for the 2014 event, do your thermal displacements align with sort of those Cavoli sightings in that table at the beginning?
They do qualitatively, and for other events, you can say say, like the 2012 off the East Coast and, in the Peru system in these El Nino years that, the order of magnitude and direction is right. But there are just a whole lot of caveats about what's actually driving distribution changes and all this kind of stuff. And difficulties on the fisheries data side, where it really does take a deep dive to be confident about that.
Sure. Thank you.
I think we have time for one more question. Okay. I don't see anything in the chat box, and no one wants to ask the final question. All right, so I think we'll end it here then. Thank you, Mike, for presenting at this month's PPAI Panel Webinar series. And a recording of this will be available next week. I'll share it out through email and on our Twitter account. So next month's PPAI Panel Webinar series is on June 17th, and we're switching over to a theme of S2S prediction and predictability. Our presenter is Michelle LaRue, one of the new PPAI panel members, and she will present on her talk, Overview of S2S Precipitation Products over the US and Sources of Skill for Wintertime California Precipitation. So I'll see you then. Thank you everyone for joining.